So from observations and laws arose the theory that all matter is composed of atoms. And those laws that brought us to matter being composed of atoms, which could also be described as atomic theory, are the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. Definite proportions and multiple proportions may appear to contradict each other, but they actually don't. So Lavoisier was the one who formulated the law of the conservation of mass. And that says that in a chemical reaction, matter is neither created nor destroyed. So when you have a chemical reaction occurring, the total mass of the substances involved doesn't change. The mass of the products is equal to the total mass of the reactants. Matter does not disappear, and it doesn't just poof appear out of nowhere. This is consistent with the idea that matter is composed of atoms. Because what happens in a chemical reaction is the atoms are still there. They've just been rearranged into a different substance. You're taking some Lego creations, you're taking them apart and making them into something else. All the Lego blocks are the same. You didn't make or destroy any Lego blocks. They're going to weigh the same. The law of definite proportions was more formally stated in 1797. And again, I'm not quizzing you on these guys' names. Joseph Proust. He was observing the composition of compounds. And he found that all samples of a given compound, regardless of their source or how they were prepared, have the same proportions of their constituent elements. So if you take water from the King's River and water from the Nile and water from the polar ice caps, and you look at the proportion of oxygen to hydrogen, it's going to be exactly the same. If you make water in the lab, it's going to have the same proportion. It's the law of definite proportions. Compounds are formed by particular ratios of their constituent elements. It's sometimes called the law of constant composition. So for water, if you take 18 grams of water and decompose it into hydrogen and oxygen, you're going to get 16 grams of oxygen and 2 grams of hydrogen. So we can say the oxygen to hydrogen mass ratio, 16 grams of oxygen to 2 grams of hydrogen, would be 8.0 or 8 to 1. And it doesn't matter how big the sample is, where the sample came from, the ratio is always the same. Because the composition of water is always the same, because it's composed of individual atoms. And the atoms combine in this same ratio. 2 hydrogen atoms to 1 oxygen atom. And so then the mass ratios are always the same. And 1804, here's John Dalton again, he proposed, or published actually, the law of multiple proportions. When 2 elements, we'll just call them A and B for simplicity, when 2 elements form 2 different compounds, the masses of element B that combine with 1 gram of element A can be expressed as a ratio of small whole numbers. So basically what that means is you can have an atom of A combining with 1, 2, 3, 4, 5, 6, some number of atoms of B. So you can get different formulas between the same elements. So water is H2O. Hydrogen peroxide is H2O2. Different chemical and physical properties. We drink water to stay alive. You do not want to drink straight hydrogen peroxide. It'll just eat you up. Not a good thing. Same 2 elements, but they're combined in a different ratio. But it's always these whole number ratios. Carbon monoxide and carbon dioxide. Another example. 2 compounds composed of the same 2 elements, carbon and oxygen. In carbon dioxide, we have a mass ratio of 2.67 grams of oxygen to 1 gram of carbon. In carbon monoxide, the mass ratio is 1.33 grams to 1 gram. So when we're talking about that law of multiple proportions, we've got this compound is 2.67 to 1, and this one is 1.33 to 1. If we take those numbers, 2.67 grams, and divide by 1.33 grams, we should get a small whole number. 2.67 divided by 1.33. 2. It's probably not obvious, but the fact that it always ends up a small whole number like that means that there is a smallest particle, the atom, and you can't get any smaller than that. And so when you combine these and make the same two elements and make two different compounds, the ratios that they combine in are always going to form small whole numbers. Yeah, I got ahead of myself. So here's the mass of oxygen to the mass of oxygen. The mass of oxygen in carbon dioxide to carbon monoxide is this ratio of 2. And that's because carbon dioxide is 2 oxygens to 1 carbon. Carbon monoxide is 1 oxygen to 1 carbon. The ratio of oxygen atoms is 2 to 1. And so their masses end up being 2 to 1. So John Dalton's atomic theory. He explained those laws of definite composition or definite proportions, multiple proportions, and conservation of mass with his theory. Those were laws. Laws say what happens. This happens, this happens, this happens. The laws were known first, observed first. And then this theory explains why those laws are. And the explanation as these points. Each element is composed of tiny indestructible particles called atoms. Now this one is not entirely true because we do know that they are destructible. But if we add in a chemical reaction, we can kind of get around that. They're only destructible in a nuclear reaction, which is a very special category. 2, all atoms of a given element have the same mass and other properties that distinguish them from the atoms of other elements. Is this principle strictly true? Are all the atoms of a given element, do all the atoms have exactly the same mass? No, they don't. There's something called isotopes. Are they really close in mass? Yeah, they're really close. So they didn't know about isotopes at this time. So that's another one that's like, not quite true. And this is a modification of a theory. So he came up with this theory, and it explained the laws, and it was accepted as true. Later, we learn more, and then we modify his theory a little bit. But atoms of the same element are different from atoms of other elements. Atoms combine in simple whole number ratios to form compounds. That is true. Atoms of one element cannot change into atoms of another element. In a chemical reaction, atoms only change the way that they are bound together with other atoms. In a nuclear reaction, they can change into other atoms. But in a chemical reaction, they can't. Chemical reaction is like you building with Lego blocks with your bare hands. You can't change one Lego into another as much as you may want to. A nuclear reaction would be you having forms and molds and heating equipment, and you could actually take some Legos and melt them down and make them into other ones. Do most people have that? Does that happen very often? No. It's a special little category. Is it possible? Yeah, but we're not talking about that most of the time.